All right, so today we're going to be going over Containment 101, understanding and utilizing air filtration systems. So, as the 101 implies, this is just a general overview of containment for those of you that may not be familiar with it at all. Hopefully, you'll learn something. For those who have at least had some exposure to it or maybe in it on a day-to-day basis, maybe it'll be a refresher for you or it'll reinforce some things you already know. But we'll go ahead and get into the agenda. So I'll do an overview of containment equipment. I'll go through some of the differences that you'll see between containment and commercial systems, just from a general standpoint. Go over some containment equipment applications. Show you some bag in, bag out containment housing examples and some bubble tight damper examples. Talk about a couple of the filter seal types that you'll find, and then go over the bag in, bag out filter change out portion of things. So when we talk about containment equipment, this is going to be equipment that you're going to find in critical applications. So these are going to be applications that utilize chemicals, biological, radiological, or carcinogenic contaminants. So things that are going to be potentially hazardous, either make you sick or potentially could kill you depending on the application. So it's going to contain that air, and it has to be high efficiency in order to contain those hazardous contaminants. So they're going to be going through a filter. That filter is going to catch it. It's going to contain it inside that housing, and it's going to isolate it in that sealed housing from any of your maintenance personnel that are going to be tasked with doing change outs and just from the surrounding environment in general. So once it's in operation, it's going to be contained by either using a HEPA filter, so a high efficiency particulate air filter, and or a HEGA filter, so a high efficiency gas absorber. And the interior of the housing until such time as it can be properly disposed of in that bag in, bag out process I mentioned earlier. So just touching on a couple of things with the HEPA or the HEGA. I know some people ask, well, how do I know which one of those I need? So a HEPA, as the name mentions, is going to be strictly for particulate contaminants. The HEGA is going to be once those contaminants are small enough to be considered a gas. So when they're in a gas form, you're going to need to have a HEGA because a HEPA isn't going to catch those type of contaminants. I have and or there because there are certain applications where you might just have a HEPA filter. Maybe you just have a HEGA filter, or maybe you have both. And when you get into HEGAs, another thing you have to think about is the time frame that the air has in contact with the carbon that's in that HEGA filter. That's going to be referred to as residence time. So the longer the air has in contact with it, the more of the contaminant it's able to take out. So you may even see some housings where you're going to have two sections of HEGA. So you'll have maybe a HEPA filter, a HEGA behind that, and then another HEGA behind that, depending on concentration levels. So containment housings are going to be constructed from high-grade stainless steel. This is especially true in the United States. There are containment housings that are carbon steel and painted. You'll see this a lot in Europe. And there are some applications here in the States that can use that. You'll see it sometimes in healthcare. But a majority of the containment housings you'll see in the United States are going to be high-grade stainless steel welded housings. They're going to incorporate a positive sealing mechanism for that HEPA or that HEGA. And that filter to housing seal is accomplished with mechanical locking bars that are going to force that filter against the internal housing seal, whether that be a flat flange for a gasket seal filter to press up against, or it's a knife edge for a fluid seal filter to press up against. And I'll show you that in a few slides. So they have to be high quality, they have to be high integrity, and they have to be high efficiency air filtration systems. And like I mentioned before, they're going to contain those dangerous airborne contaminants, both gaseous and particulate, and they're going to isolate them until you can dispose of them properly. You can see in this picture just one variation of several that you might come across in the field if you're looking at doing a change out of existing units, or what you may find if you're helping an engineer design these or something like that. So it can be anything from a 1x1 unit with a pre-filter and a HEPA filter up to 5 filters high, 6 filters high, 3 to 6 filters wide. So it runs the gamut on size. So some of the things you'll see from a component standpoint with containment housings. So you're going to generally see pre-filters, HEPA filters and or HEGA filters. The filter housing itself that holds those filters. Depending on the application, you may have test housings that are connected to these filter housings. Those test housings can either be an overall efficiency test housing, or it can be a scan test housing where you're actually moving a probe over the face of that filter to test for any pinhole leaks. You'll generally have dampers, which will be bubble tight dampers that can be closed for either decon of the housing if it's in a biological application, or just for filter change out and safety. And that standpoint, you can make sure that housing is shut down completely before you do those things. I've got ductwork here in bold. Generally, the housing manufacturers aren't supplying the ductwork for these, but something that you have to keep in mind, especially if you're working with somebody designing a system, is you can have the best containment housing in the world, but if you're not attaching ductwork that's of the same quality, then you're going to have leaks in that ductwork. So the ductwork has to be high quality as well to match the performance of the housing. And then I've got fans on here as well. Not every application is going to require fans, but you'll see in a few slides when we get into some of the healthcare applications for isolation rooms, there might be fans attached directly to these housings to help pull air through. So the heart of the containment system is going to be the filter housing and the filters that go in that housing. The most common type of containment housing used is going to be the bag in, bag out housing. It's going to be generally a side access housing. And the bag in, bag out feature of that is what helps protect that maintenance personnel. So during that bag in, bag out procedure, they're going to be protected from what's inside that housing while doing their filter change out. And this is where that NCT2 certification that was mentioned earlier comes into play, and knowing how to do that bag in, bag out change out safely. And just to go over some of the pictures that you see here. So this would be a general side access bag in, bag out housing. This particular one has dampers on it. It's got decon ports on it. It's got a pre-filter door. It's got a HEPA filter door. This particular housing has a scan section door on it. So there's a lot of different variations of housings that you'll see, and different types of test systems that go on these. But this is just one that you may come across in the field. This here is a low flow, higher pressure type housing. Would generally just hold one filter and can withstand some higher pressures than maybe a side access housing would. And then this is a vertical bag in, bag out that you would generally see in a pharmaceutical company that might be doing potent compounding or something like that, where on the room side, you'll have a a nice finished cosmetic door, and then you open that door, and behind it you'll see the vertical bag in bag out doors where you can actually do a filter change out of the filters that are in there. So getting into the differences between containment and commercial systems, it seems like in my time in the industry, a lot of people are more familiar with the commercial systems, but are a little fuzzy when it comes to the containment side of things. So just from a general standpoint, the standard design pressure of containment housings is going to be at least 10 inches water gauge, versus roughly 3 inches, give or take, on commercial systems. These containment housings at that design pressure are actually going to be pressure decay leak tested to 0.0005 CFM per cubic foot of housing volume at that 10 inches water gauge, or whatever that design pressure that housing is. These housings can generally be reinforced to go to higher pressures as well. So you can do 30 inches, 60 inches, 80 inches if need be. And that pressure decay leak test would be done per that design pressure. They're going to be designed, manufactured, and tested under strict quality programs. One of those you may come across if you're reading a spec is going to be ASME NQA1. So this is the nuclear quality assurance program that the Department of Energy uses. These are going to be all welded construction. You may see commercial systems that are either tack welded and caulked or maybe bolted and caulked, but containment housings are going to be all welded construction. Most containment housings are going to be bag in, bag out again to protect that maintenance personnel and the surrounding environment. They're going to be a high integrity design. So that filter locking mechanism that maintains that filter to frame seal throughout the life of the filter is going to be designed to make sure that that seal stays the same throughout the life of that filter. That's especially true on a gasket seal filter. As a lot of you probably know, a gasket can lose its memory over time. And a lot of these housings are designed to keep a consistent pressure on that. So even if that gasket starts to lose its memory a little bit, it's going to have a constant force pressing against that to make sure it maintains that HEPA integrity seal. Stainless steel construction, especially here in the States, each tier of filters is going to have its own access door on a containment housing. So you may see a commercial system that's 3 high, and when you open that door, you see all 3 tiers of filters when you open that door. On a containment housing, you're going to have individual doors per tier. So if it's a 3 high housing with HEPA filters, you're going to have 3 separate doors to get access to that tier of HEPA. And that helps in the safety of doing filter changeouts. That also helps with being able to maintain those higher pressures as well. Most of these are going to have filter removal rods, especially if you have a 2 wide or a 3 wide housing. And that comes into play, especially when you get into the bag in, bag out process. So when you're doing the bag in, bag out process, you're doing that through a PVC bag. And you don't want to have to try to reach way into that housing to try to get that filter out and risk tearing that bag. You want to be able to bring that filter to the opening so you don't have to reach in. And that's what those filter removal rods help you do. And they also have an integration of isolation dampers, which allows the decontamination and or safe change out of the filters versus a commercial system that generally does not have that. So some of the containment system applications are places where you'll see containment systems in use. So you're going to have biosafety, the nuclear industry, whether that be the Department of Industry or nuclear power, chemical plants, government facilities, the military, so Department of Defense, Homeland Security. The space industry uses containment housings, and they may not use a bag in, bag out, but they may use a containment housing for the pressure that it can withstand. Universities and all the university research labs, medicine when you're dealing with like nuclear medicine and things like that. And then there's several others out there that you'll run across as well. So this is a layout of a biosafety life science application. So you'll see in this rendering here, down there at the bottom, you'll see these isolators are typically going to be your primary barrier in this type of application. And then you'll have bag in, bag outs installed as a secondary containment barrier in case of an event. So if one of those isolators fails, you'll see there's a low wall return duct here going up to a bag in, bag out housing to be exhausted. Or you may have a low wall bag in, bag out containment housing in the wall that's exhausting. Depending on the application, what's being done there, and what the safety officer's choice is, 100% exhaust or returned with double HEPA. Generally, it's a good idea to do 100% exhaust, especially depending on what's going on in that room. And then from a supply standpoint, you'll generally find terminal housing supplying the clean air to that room. So here's a rendering of a healthcare isolation room application. So this is an airborne infection isolation room. And I believe it was Tony mentioned earlier, one of the guidelines that he mentioned was a airborne infections and healthcare guideline, which goes over some isolation room information. But in this type of room, there's an isolation technique used to prevent contaminated air, room air from leaking into adjacent spaces. So they're using a cascading negative pressure zone to ensure clean air is pulled into and through the room and contaminated air is effectively removed instead of air moving out of that room and into your anteroom or into a hallway. So air is always going to be moving towards that patient room and then pulled out across the patient and away from the entrance of the room. And that's an important aspect as well, that you want that air coming over your patient and into this area of the room instead of your return being over here where the air is being pulled back into this area to be exhausted out. You want that to stay pulling over the patient and out of the room and away from any of the entrances. And then you'll generally have some type of terminal housing supplying the air to that as well. This right here is an example of the containment units with an integrated fan that you'll see a lot on isolation room applications. So from a bag in, bag out containment housing example, this rendering here in the top right hand or left hand corner is going to be a typical arrangement for an isolation room. So on this one, you've got your damper, you've got a pre-filter, a HEPA filter, and then you've got your fan pulling that exhaust and exhausting it out. This housing on the top right, you would see more for a biological application. You'll see on the transitions here on each side, there's decon ports. The reason those decon ports are in there is generally in a biological application, before you do any filter testing or filter change out, you're going to want to decon that housing to kill whatever's in there. And there's different companies out there that make equipment to hook up to these to perform that. And they're injecting things like vaporized hydrogen peroxide or chlorine dioxide. So there's different things they can put through that housing. And depending on what's in that housing, there's a certain amount of time that they're going to run that through so they can get the log kill that they want on that particular organism, to render it basically inert or killed, so that you can do a more safe change out or test of the filter on those housings. This one down here would be for a nuclear application. You can see just some of the size differences in just these three here. But depending on what the customer needs, a lot of different manufacturers can do different metal work to accommodate their space or specific requirements. So you'll see in this particular housing, instead of air going horizontally throughout the entire housing, the air entry is actually on the top of the housing. So it's actually coming in, making a 90-degree turn to go through the housing, and then making another 90-degree turn to go out of the housing. And you'll see in this housing that each tier has its own damper shutoff. That's used for redundancy purposes. So it may be that this housing, the rated flow can be achieved with just 3 tiers of those. That way you can shut off one tier, do your filter change out without actually interrupting the flow of air through the housing. That way that housing's never actually down. Once you've got that tier changed out, you open it back up, you close your next tier, do your filter change out on that next tier. So you can segregate each tier to do filter change outs without interrupting the flow of air through the entire housing. These down here would be for a nuclear application. These are some round housings. And again, the round housings will generally be seen when you have some lower airflow, but you have a much higher pressure requirement than a site access can take. These are just some other variations. These would be for biological applications. You'll see all of them have those decom ports on it, but you'll see like this top right hand one, air is actually coming in, making a 180-degree turn and coming back and then going out the floor. So a lot of different variations in how these housings can be assembled together to accommodate the mechanical space. You'll see this housing down in the bottom right-hand corner. It's got some angles that are actually welded on to the transition. So this is a good example of a housing that has a little bit of a higher pressure than that standard 10 inches for containment housing. So this had a higher pressure rating, so reinforcements were put on that housing to make sure it could withstand that pressure rating. And then you'll see on this housing, air's coming up from the floor, making a 90-degree turn to go through the housing, and then making another 90-degree turn to go out the ceiling. It's got its decom ports on there. Some of these housings you'll see have manual dampers, like these two here. This particular housing has a manual actuator on it, but it's a override for that manual actuator. It actually has a pneumatic actuator on it. So on these dampers, you can do just manual actuators, electric actuators, pneumatic actuators. When you get into the electric and pneumatic, you can get into fail-safe options where it's either fail-safe open, fail-safe close, or double acting. That way, if there's a specific event, if you lose power, you can make it to where the damper automatically closes on a loss of power. So there's some different variations depending on what the customer needs when it comes to dampers and the actuation of those dampers. Here's some examples of bubble tight dampers you may see. So you may see round, flat blade bubble tight dampers. You might see dish blade type dampers. These dampers can be installed in ductwork by themselves, or they can be used in conjunction with the containment housing. This particular containment housing has it bolted onto it. but you may see these welded onto housings. If you do get dampers that are part of the housing, generally this is going to be tested as a system before it leaves the manufacturing plant. So the manufacturer will make sure that as a system, damper flange to damper flange, it's going to perform to the pressure that it needs to perform to. So when it comes to filter seals, there's two different filter seals that you'll see with containment housings. One of those is going to be a fluid seal. That's what you'll see here on the left-hand side. So that fluid seal utilizes a knife edge in the housing, and then you'll have a trough in that filter or a track in that filter that's got a fluid seal gasket. And as that filter moves onto the knife edge, that knife edge is going to go into that fluid seal, and it's going to create the seal that you need for the HEPA integrity. That's done utilizing some type of locking arm or locking mechanism that you would actuate. And generally, when you have a fluid seal filter in a site access containment housing, you'll have what's known as an extractor clip. And what that extractor clip does, it's attached to the filter itself, and it'll actually ride on an angle in the housing that's attached to that locking arm. And as that locking arm is actuated, that bar is going to actually either pull on that extractor clip or push on the filter to get it off and onto that knife edge. And that just ensures that filter gets pushed evenly onto that knife edge and gets pulled off of that knife edge evenly. Because the last thing you want to do in a containment housing is have your filter get a little bit turned, and now your knife edge is acting like a bulldozer, and it's pulling your fluid seal out when you take that filter out of it. Now you got to worry about figuring out how to get into that housing that's contaminated and cleaning off your knife edge so that you could put your new filter in there so that it has a good seal. So that's what those extractor clips are used for on filters for fluid seal housings, is just to ensure that filter will get pushed onto that knife edge and pulled off of that knife edge evenly so you don't have that issue. The other one is going to be a gasket seal. So this would either be a neoprene gasket, or it could be like a core elastic sponge gasket if you were dealing with higher temperatures. But there's going to be a flat flange in that housing that filter is going to push up against, and that gasket will push up against that flat flange and compress to give you your good seal. And then you'll have some type of filter locking mechanism that you're actuating on the top and the bottom to press that filter onto that flat flange. You'll see in this particular instance, there's a bar right here that's actuated, and then there's another bar that's attached to the front of it that has springs in between it. So as that bar is pushing against that filter, it's going to compress that filter and that gasket onto that flange, and those springs are going to provide the tension that it needs to ensure that over time, as that gasket begins to lose its memory, there's constant pressure on it, so it's going to keep that HEPA seal. When it comes to HEPAs and figuring out what HEPA you need, there's going to be different efficiencies. So a general rule of thumb is for nuclear applications, you're generally going to see filters that are 99.97% efficient. For bio and life science, you're going to see filters that are 99.99% efficient or higher, depending on what you're filtering out. When it comes to picking either a HEPA or a HEGA, remember I mentioned particulate would be your HEPA. So if what you're moving is a particulate HEPA filter, if it's more in that gas range, you're going to have a HEGA to effectively remove that. I know sometimes we get the question of isotope removal. So Isotopes can be either a gas or a particulate. So if you run across that question from an end user, from an engineer, just find out what the contaminant it is specifically. Reach out to your manufacturer, and that manufacturer should be able to help guide you through the process of figuring out, all right, for this, you're going to need this type of filter. For this, you're going to need this type of filter. But from a general rule, particulate's going to be HEPA, gas is going to be HEGA. And both of those come in either a gasket or a fluid seal design. When it comes to the bag in, bag out process, so the bag in, bag out process is going to be used for changing out those filters. And you'll see in this picture here what I'm talking about with the bag. There's going to be a variety of sizes out there depending on the manufacturer, depending on the type of housing, the door configuration, the size of the housing. But there's a lot of different sizes out there. What you may see or people refer to is going to be the circumference and the length of the bag. So you may see somebody reference a 90C by 96 bag size. Bags are generally going to be made from 8 mil PVC, and they're going to be rated for temps of 0 to 130 degrees Fahrenheit. There are other types of bags out there that will withstand higher temperatures, Teflon type bags. That's definitely something you want to make sure of before you go to order filter or order bags for your change out, because some of the price differences between a standard PVC change out bag and some of those higher temperature bags can be pretty drastic. So make sure when you're talking to a customer or you're reading through a specification, you pay attention to whether or not it's a high temperature application or not, and what that temperature range is. And if it doesn't mention a temperature range, make sure you ask the question. So there's going to be security straps that hold these bags on the housing. That's going to be this B area right here. So on a bag in, bag out housing, you'll have what's called a bagging ring at that door opening. And that bagging ring is going to hold that bag onto the housing, and that security strap is going to help make sure that bag stays on. So the bag itself will have almost like a bungee cord hemmed into the end of it. It's going to go all the way up towards the front of that housing, and then that security strap is going to be in between a couple of ribs on that bagging ring. So there's also going to be a cinching strap, and that's going to be what you see here, which is C. Basically, the cinching strap is going to prevent that bag from being pulled into the airstream. So if you don't use that cinching strap and you get your filters in, you get your bags on, you close your door, you turn the system on, and all of a sudden your magnehelic gauge pegs out, probably because that bag got pulled into the airstream because the cinching strap wasn't pulled on. So that cinching strap helps prevent that bag from being pulled into that airstream, so that air runs through that housing like it's supposed to. When you go to do your changeouts, each changeout is going to require 2 bags for each filter being changed -1. And it's -1 because there's generally going to be 1 bag already installed on that unit when you go to do your filter changeout. So general rule of thumb, 2 bags for each filter being changed -1, and that's per tier. So that's not per housing, it's per tier of that housing. The security and cinching straps can be reused as long as that Velcro that attaches them still catches. Once that starts getting worn and not working properly, you'd want to reorder those as well. And as Tony mentioned earlier, NAPA does offer a certification in bag in, bag out filter change out. It's the NAPA Certified Technician Level 2. And you'll see a link there to the NCT2 page on the NAPA website where you can get some more information and register. So there's 2 opportunities to take this class in 2024. The first is currently scheduled for July 31st, and the second scheduled for November 13th. I believe the July 31st one is in Chicago, and the November 13th one is in Washington, North Carolina. There is a prerequisite for that, and that's to go through the NCT1 certification, which can also be found on the NAPA website. So with that, I will turn it back over to Matt.
Great, Andrew. Thank you very much. That's a ton of information, and we got a lot of questions. I'm going to start out with a couple right off the bat. The procedures to conduct certification after filter replacement. So what are the procedures to conduct certification after replacement of filters?
Okay, so once you do a filter replacement, there will be the test housings I was referring to earlier. So the test housings are going to be either an overall efficiency test housing or a scan test housing. So you'll have to have a way to inject your aerosol for your testing. That can either be done through a what's generally referred to as a test inlet housing that's part of the housing, or it can be injected upstream of the housing. There's a general rule of thumb in the industry that you can do that 10 duct diameters upstream of the housing. There are some caveats to that. That's not a validated test, and it kind of goes under the assumption that that 10 duct diameters is a straight 10 duct diameters with no turns or bends or anything like that. So that's why it's always a good idea if you're doing something from a new construction standpoint, asking the question of, hey, are you all going to need to do any validation of these periodically? If so, we recommend doing this, and they can have that test housing added to their containment housing. But if they don't have that, they can use that 10 duct diameter rule of thumb to inject their aerosol. They would also want to have a way to get their upstream concentration of aerosol before that HEPA filter. That way they can compare that to what they see downstream of that HEPA filter in either the overall efficiency test or in the scan test. So they're going to use a photometer or a particle counter to do that portion of the test. But that's how you do a validation of your filter change out to make sure that it was done properly, everything's sealed in good, and your filters are performing. That's also a way you can make sure your filter's still performing if it's not time to change your filters out. So a lot of times on commercial systems, it's always you change your filters out on pressure drop. So general rule of thumb is double the initial pressure, or what your fan can handle, whichever one's lower. But there may be certain applications, especially in containment applications, where you may not be at that final pressure drop yet. But if you do that scan test of your filter in a biological application, you may have a filter that's not performing like it's supposed to. And in certain applications, that can be a bad thing. So you might want to change your filter out before it reaches that double the initial pressure. So double the initial pressure drop is a good rule of thumb, but in containment applications, it's always good to have those test housings available to validate that system.
Great. Awesome. Okay. We got actually quite a few questions coming in along the lines of the selection of the correct filter. You mentioned a couple different efficiencies of HEPA, but what's the process to selecting the correct filter for these systems?
So that's that's generally going to depend on the application, really. As I mentioned before, a general rule of thumb is for nuclear applications on HEPA filters, you're generally looking at 99.97%. For biological life science applications, you're generally looking at 99.99%, or higher, depending on what you're trying to remove and what the particle size is. So that comes into play is the contaminant that you're actually trying to remove. But rule of thumb, 99.97 for nuclear and at least 99.99 for bio life science applications. If you're going with HEGAs, because it's a gas type application that you're trying to remove, that's when you're going to have to know what your contaminant type is, because a lot of people know of carbon filters and they think activated carbon, that's good to go. But different carbons can be impregnated with different things to ensure that it takes out specific contaminants. So whereas activated carbon may be okay at taking out a certain contaminant, if it's impregnated with something else, it may be a whole lot more efficient at taking that out. And again, you want to know concentration levels of that contaminant as well. And that'll depend on like how deep your beds are, how deep your HEGA is, because when you get into your HEGAs, you're dealing more with your residence time. So you want that contaminated air to be in contact with that carbon for as long as you can during that pass, so it has more time to take out that contaminant. That's why you generally don't run a system with HEGAs at 2000 CFM, like you might be able to get away with a HEPA filter.
There was a couple questions that kind of tie right into that with pre-filtration and like how important it is. There was a question about how important it was and how often it has to be changed, selecting it in these different applications. So on the pre-filter side, are we really concerned? Is there a big implication on making sure we have the right one there?
Pre-filters are definitely a good option to have on containment housings. Again, that's going to be a lot of times up to the customer. Sometimes it's going to be up to space constraints, whether it's going in a mechanical space where you may not have a lot of room. But generally, we see like a somewhere between a MERV 8 and a MERV 10 pre-filter, maybe 2-4 inches. There are times in certain applications where you'll see a MERV 11. I've seen other instances where the customer wanted to have a 2-inch pleated pre-filter. They wanted to have a 12-inch medium efficiency MERV 14 ASHRAE grade filter, and then they wanted to have their HEPA filter. So a lot of that just depends on the customer and the application. But keep in mind, if you do have pre-filters, it will always protect your HEPA filter from some of the bigger particles. And it's a whole lot better to change out a cheaper pre-filter than it is to change out a more expensive HEPA filter. And again, on the pre-filter side of things, that's generally going to be done off of either pressure drop or a PM schedule. It might be that a certain site they're automatically going to change their pre-filters out every 2 months or every 3 months, whether it's reached its max on its pressure drop or not.
Sure, that makes a lot of sense. Great. So, do you need do you need a license or certification? I'm trying to combine some questions here. Do you need a license or a certification to install or maintain these systems?
You don't have to. However, it's a good idea to get certified to do it so that you know what you're doing. I've had some people come through the NCT2 class who had not gone through it before, but had been out in the field to do bag in, bag out change outs. And there were some items where when we were going through it, the light bulb went off in their head, kind of like, I wish I had known that previously. So there are people out there doing bag in, bag out change outs without being being certified or having gone through some type of class. But it's always a good idea to go through that class to make sure you're covering all your bases and thinking about things that you may not have thought about previously.
Absolutely. For the end user and the person changing it out, right?
Correct.
So there's you mentioned a couple standards, and there was questions on whether they were if the filter manufacturer was supplying the housing and to the standard that was requested for the installation. How is that tested and validated?
Okay. Can you repeat that one again?
Yeah, sure. I'm combining a couple again.
Okay.
But so the filter manufacturers, well, first of all, are these filter manufacturers supplying these housings to a specific standard?
Okay. Yeah. So most of your manufacturers are going to supply these based off of a certain quality standard, especially if that quality standard has been invoked in the specification. A lot of specifications will mention ASME and QA1 or built per a certain section of ASME AG1, which is the code on nuclear air and gas treatment. But most manufacturers have a quality program that is going to be able to meet those criteria.
And are
so
they?
that is a good question, because you definitely don't want to just run across a local sheet metal guy that's trying to build a containment housing that's never done it before. So yeah, make sure you're checking those manufacturers to make sure they are doing that under a quality program.
And are these great answer? Yeah, that's a really good point. Are these tested or validated after the installation at any point?
Yeah, so a lot of times once these are installed, there's going to be a testing company that comes in. Generally, it's going to be a third-party testing company. That way, you remove any question of the manufacturer coming in and doing it themselves. But a lot of people are going to hire a third party, or they may have the ability to do the testing themselves in-house, depending on the end user. But they'll validate that it was installed correctly. They'll probably do a in place pressure decay leak test on it, and they'll test the filters if they have the test equipment to do that on the housing. That way, they know they've got a validated system from the manufacturer, and when they installed it, everything was installed correctly before startup.
Great. Okay. A couple questions on dampers and actuators. Combining them, is there a standard requirement for a bubble damper or for some sort of fail-safe closed actuators, or is it dependent on the end user specifying that?
A lot of times it's dependent on the end user and what they're wanting to happen in the case of an event. Some places, depending on the application, are completely fine with just the manual hand wheels, but some of your higher level places, such as like BSL3, BSL4 labs, generally aren't going to have just a manual hand wheel to actuate. They're going to have the electric actuators with fail-safe options on there, so that in the case of an event, the dampers can close. That way, there's no chance of what's going on in that lab leaking out. Because when you're dealing with BSL3, BSL4, you're dealing with things that potentially may not have a cure if you catch it. So
makes sense. I think we'll do maybe one or two more here. Once a system's installed and standards are raised, there was a couple mentions of COVID and recent changes in standards and regulations. Are these systems ever grandfathered in, or do they constantly have to be updated as these standards change? it was a curveball. That's why I was curious
Correct.
too.
Yeah. No. So the answer to whether or not COVID made it to where these housings had to be um, updated or upgraded to react to COVID, the answer to that is no. These systems were made specifically to do things like that. COVID's just another one of the contaminants that a containment housing can catch. It just happened to be for the COVID outbreak, there was some kind of breakdown or failure in a facility somewhere. So from a manufacturer standpoint, when COVID happened, there didn't have to be an update to containment housings in order to react to COVID. If I understood the question correctly.
I think so. I again, I've combined a couple there. There's been a lot of questions and a lot of very technical stuff, which is great to see that there's some really good engagement here. Last question. Some people were asking, how do they know, or who do they ask to find out if they need a system like this, specifically in a private industry? Is there somewhere that they can turn to find out what the best practices or rules and regulations are for their industry?
Yeah, so there's a lot of different things out there that kind of give guidelines on what's required. So I mentioned ASME AG1 earlier for the nuclear industry. So it's the code on nuclear air and gas treatment. But the CDC and National Institutes of Health also have guidelines out there for designing in biosafety applications. There's also organizations like ABSA, the American Biological Safety Association, that's got a lot of good information on what you need. And then there's also the manufacturers. There's people you can reach out to that can answer a lot of those questions for you as well.
Fantastic. Okay. Well, I learned a lot. I got a whole page and a half of notes that I'm excited to try to grab some more answers from you down the road. Is there anything else before we wrap up with Tony, before we close out, that you want to add to this? I'm good. I was excited. Good. Tony, I'll hand it off to you.
Good. Perfect. All right. Well, thank you, gentlemen. Thanks so much. Thanks, Andrew. And thank you, Matt, for getting technical. This is exactly the sort of stuff that NAFA does, is kind of get into the weeds sometimes, and the weeds are important as well. So thanks for doing that. And Andrew, I also, while you had mentioned at wildfire smoke, I thought, oh, you know what? We've done a webinar on that. So I just shared on social a webinar we did in the past about wildfire smoke. So if you're so inclined want to learn about that, go back into the archives and watch that. So again, thanks so much. We did record this. We will put this out on our website. There's a webinar page for that. We'll actually put it on our podcast as well. So in case you missed it, or you thought it was interesting enough to share with someone, that would be great as well. So thanks, gentlemen. I will gather up some of these questions, and Andrew, I'll send these over to you. So if there's anything that maybe you want to answer with some of this folks here that we didn't get to, I'll share those. So if your question wasn't answered, we'll definitely have Andrew look at those and see about possibly getting back to you on those as well. So yeah, thanks so much. Absolutely. All right, fantastic. Thanks everybody. Thanks for a great one, and we'll see you on the next one. See you in June for the Dominating the Digital Domain webinar. Take care.
Thanks. Take care.
Thank you.